Hello everyone. Today I'm going to talk about the effects of data intertwinedness on deep neural networks fragility, a work done by me and James Zhu at Stanford University. We are going to discuss three key concepts of this work: the well-known deep networks fragility, intertwinedness of data, and deformation of space through a deep network. We know that conventional deep networks map the input space in which the data samples lie to a linearly separable space located at the pre-softmax layer of the network, most of the times called the representation space, or as we're going to call it, the score space. The assumption is that the more intertwined the data points are in the original space, the more space deformation the neural network will cause between original and score space, which makes the network more fragile. Intertwinedness is simply the ratio of neighbor samples of an average test data point that do not share the same label with it. We have used two simple measures discussed in our poster. As an example, in figure A and B, the intertwinedness of CFAR10 and MNIST are depicted respectively, and it's clear that CFAR10 is a much more intertwined dataset. In both cases, the resulting score space is a completely non-intertwined space. This change could not be achieved without deformation of space. We have introduced two methods to measure deformation. In the first one, we rank the distances of n pairs of test data points in the input space. We then examine how the ranking of the same pairwise distances has changed in the score space using the Pearson's rank order correlation. Smaller correlation means more deformation. The second method is discussed in the poster. To examine deformation alongside training, for CFAR10 dataset, you see that more number of layers resulted in more space deformation. It's also important to notice that all three networks have a smaller and nearly the same deformation after random initialization and before training, which means that big space deformation is not an inherent feature of deep networks. Also, it could be seen that space deformation is not affected by overfitting. We also created our own synthetic datasets with different measures of intertwinedness to test our hypothesis. As displayed in the plot, the more intertwined the training dataset is, the more deformation the neural network will cause. To measure fragility, we use the simple fast gradient psi method. Each dimension is perturbed in the direction of the sign of the gradient of the loss function. We then track the L1 norm change in the output probability vector of the deep network. More change means more fragility. As we had hypothesized, increase in the data intertwinedness means increase in the network's fragility. All in all, we showed the relationship between data intertwinedness, space deformation, and network's fragility. Please visit our poster for more information and discussion. Thank you very much for your time.